Hello, and welcome to part 5 of my read and work through of Generating Functionology by Herbert Wilf. Last thing I finished was working through the example of fitting the cubic spline function to the first 5 roots of powers of 2, and that took quite a bit doing, so let's carry on. One reason why you might like to fit some numerical data with a spline is because you want to integrate a function that the data represent. I guess that's correct grammar, isn't it? Because data is a plural. So, yeah, interesting. The data represent. I would have thought data represents, but I guess that's probably wrong. Integration of 1.4.7. That was the formula for SIX. So I'm gonna write that down because I'm gonna want to integrate that. So SIX equals 1 over 6h zi ti plus 1 minus x cubed plus zi plus 1 x minus ti cubed plus 6yi plus 1 minus h squared zi plus 1 x minus ti plus 6yi minus h squared zi ti plus 1 minus x so integration of 1.4.7 from ti equals ih to ti plus 1, which is equal to I plus 1h, shows that the integral is h over 2 yi plus 1 minus h cubed over 24 zi plus 1. So I want to check this. That's pretty cool because it's a very simple form of the integral there. We know what h is in advance, we know what the yi's are in advance, and we know what the z's are going to be once we've solved the linear equation. And that's pretty cool because that means that, oh no, we don't know what the yi's, hold on, so the yi's are the values that the function takes, that we're trying to approximate takes at ti. So yeah, we do know those in advance. So yeah, all we need to do is find the zi's, and we don't need to actually calculate the spline functions themselves to get this integral. So let's try and check, see if I agree with what they have. So the integral from ti to ti plus 1 of SIX dx is going to be equal to 1 over 6h. That's going to be on the outside for sure. A big bracket because this is probably going to get a little bit messy. So if we integrate, what you do is we raise the power by 1 and then divide by the new power. So we're going to have zi ti plus 1 minus x to the 4, and we're going to have a 1 over 4 on the outside, but because this term here, the x is it's minus x here, we need to take the minus out as well. And the next bit is going to be plus 1 over 4 zi plus 1 x minus ti to the 4 plus this is going to become an x squared term, so we're going to have half 6yi plus 1 minus h squared zi plus 1 x minus ti squared plus, it's going to be minus a half 6yi minus h squared zi, get rid of that space, ti plus 1 minus x squared, just fit it in there. And we are integrating between ti plus 1. So if I plug in ti into, well, let's plug in ti plus 1 into this integral here. So it's 1 over 6h. Plug it in ti, this term vanishes, good. And this term doesn't vanish. So you're going to have 1 over 4 zi plus 1. So ti plus 1 minus ti is h, so h to the 4. Now we're going to have plus a half 6yi plus 1 minus h squared zi plus 1 h squared, and then this term vanishes. And we're also going to have minus the integral evaluated at ti, so minus 1 over 6h. And this time this term is minus a quarter zi h to the 4. This term vanishes. This term vanishes. Minus a half 6yi minus h squared zi h squared. So this should be the integral. Let us see what this works out to be. So it's 1 over 6h. So you've got a quarter, span these brackets out, quarter zi h to the 4 plus 3yi plus 1 minus a half zi plus 1 h to the 4, and then we've got a minus and a minus here, so I'm going to change them both to pluses. So plus a quarter zi h to the 4 plus 3yi h squared, I missed this h squared out, minus a half zi h to the 4. Okay, so this should simplify a little. So we've got 1 over 6h, have a quarter zi h to the 4 minus a half zi h to the 4, so that's just minus a quarter zi plus 1 h to the 4 plus 3yi plus 1 h squared. And then we have a quarter zi h to the 4 minus a half zi h to the 4, so that's minus a quarter zi h to the 4 plus 3yi h squared. So let's see, and we've got this 1 over 6h, so we're going to have minus 1 over 24 zi plus 1 plus zi times h cubed plus a half, so 3 over 6, a half, yi plus 1 plus yi, h, just h. Is that what they had? They had h over 2, yi plus 1, yep, and minus h cubed over 24, zi plus 1. Great, so we agree. So that's pretty cool. So like I say, so we don't even need to work out, I mean, the easiest part of the problem was actually calculating the z, especially with the simple formula that I had for calculating them. it was less nice calculating the actual cubic functions, and I got a computer to do that for me because the coefficients were a bit messy and it was a bit difficult doing that by hand. So yeah, that's pretty cool. I wonder if it's easier to solve for zi plus zi plus 1 than actually solving for the individual zi's, because to calculate these integrals we only need to know the sums of adjacent z's. I know that we have a relationship telling us, what was it? It was zi minus 1 plus 4zi plus 4zi plus zi plus 1 was equal to something. So that doesn't give us an easy way of calculating the sum of zi and zi plus 1. But maybe there is an easier way of doing it than calculating the individual zi's first. Who knows? So, integration of 1.4.7 from ti to ti plus 1 gives us this that we just verified. Thus, fitting some data by a spline and integrating the spline amounts to numerical integration by the trapezoidal rule with a third order correction term. So, what's the trapezoidal rule? I'm guessing that it means, if this is our function that we want to integrate, and here is the x-axis, and this is ti plus 1. Maybe that's a bad place to do the example. Ti there and ti plus 1. I think it means that we are calculating the integral by taking the areas of these trapezoids, trapeziums, or whatever they're called. And the area of this, if this is yi and yi plus 1, it's going to be, well, the area of this square here, which is, then the width is h, so it's going to be h yi plus 1 minus yi plus the area of this thing here, which is yi plus 1 minus yi. Ooh, no, I did this first bit wrong. The area of this first one is just hyi. The area of the second bit is yi plus 1 minus yi, so that this height here, times h over 2, because we've only got half of this square. And this should work even if yi plus 1 was less than yi, because you would then be subtracting the area of this triangle away, so it would be fine. And simplifying this, we get a hyi minus hyi over 2. It just becomes h over 2 yi plus 1. Okay, so the first half of the formula was h over 2 yi plus 1, so that must be what it means. So this is numerical integration by the trapezoidal rule with a third order correction term, and so the third order correction term must be for minus h cubed over 24 zi plus zi plus 1. Okay, so if we sum 1.4.12 over I equals 0 to n minus 1, we get the overall integral. So they've got integral from 0 to nh of function sx is equal to Well, let's try and calculate it. So, see what we get. Right. So, we're summing from, right, so we're going from 0 to n minus 1. So we're going to have, so how many blocks are we going to have? We've got t0, t1 up to tn. I don't know, so it's, yeah, so it'll be n minus 1 in this case, because there'll be n minus 1, there'll be n different chunks, so summing from 0 to n minus 1 gives us the n different chunks. So, and it's the sum of h over 2 yi plus yi plus 2 minus h cubed over 24 zi plus zi plus 1 equals so what do they have? How do they have it? They have, okay, so they've got something plus the 0, 1, n and n minus 1 terms. So let's see. So what's this going to look like here? I'm going to split it into two separate terms. So h over 2, sum from I equals 0 to n minus 1 yi plus 2. It should be yi plus 1. Why am I writing yi plus 2? Don't know where that came from. And then minus h cubed over 24, sum from I equals 0 to n minus 1 zi plus zi plus 1. And if we work out this sum, I should imagine it's going to be h over 2 well, you're going to get a y0 at the beginning, and then you're going to get plus 2 y1 plus y2 plus dot 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 to yn minus 1 plus yn, because everything in this range gets repeated twice. The endpoints only occur once, and it's going to be the same for the zi. So h cubed over 24 z0 plus 2 z1 plus dot 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 zn minus 1 plus zn. Now, I know in advance that we know in advance that z0 and zn is 0. Oops, that should have been inside the bracket. Zn and z0 are 0, so I can cross those out. So here I've just got h over 2 y0 plus 2 y1 plus dot 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 yn minus 1 plus yn minus h cubed over 24 times 2 z1 plus dot 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 plus zn minus 1. Okay. And what they have is if we sum over 1.4.12 over I from 0 to n minus 1, we get the overall integral blah blah blah. What's the h cubed over 72 coming from? It's a factor of 6 has appeared. 72 is, I think, 6 times 24. What is it? Not sure. in which trap is the trapezoidal rule and the z1 and the zn minus 1 satisfy the equation from before. How are they getting this? Are they using the linear equations that the z's are supposed to satisfy to get it into this form? Perhaps they are. So we know, well, this is the section from the trapezoidal rule. This is the trap, as they're calling it. They're calling this part is just trap. Okay. And this bit here is the other bit. So this is going to be equal to trap minus h cubed over 12 times z1 plus dot 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 plus zn minus 1. Aha, I think I'm onto this now. So, and the equations that the z solved is for I equals 1 to n minus 1, that zi minus 1 plus 4zi plus zi plus 1 equals 6 over h squared yi plus 1 minus 2yi plus yi minus 1. What do we get if we sum all of these together? So sum from I equals 1 to n minus 1. This is going to be, so it's going to become z0 plus z1 plus dot 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 plus zn minus 2, because when I is n minus 1, I minus 1 is n minus 2, plus 4 z1 plus dot 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 to zn minus 1 plus z2 plus dot 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 to zn. And this is going to be equal to the right hand side, all summed from I equals 1 to n minus 1, so 6 over h squared. It's going to be y1 you know it's going to go from y well, if I start with this one, that's going to be y0 sum from y0 to yn minus 1 and minus 2, sorry, plus minus 2 sum from y1 to yn minus 1 plus sum from y2 to yn. Alright. So, what is this? I think we can simplify the top and the bottom here. So, if I let, I'm going to call S Z, subscript Z, to be the sum from j equals 1 to n minus 1 of zj. So this top bit here, remember that z0 is 0 and zn is 0. This top bit here is going to be, first term is sz minus zn minus 1, sz minus zn minus 1, plus 4sz, plus sz minus z1. And if I call the sum from y equals 0 to y sorry, from y0 to yn to be sy equals the sum from j equals 0 to n yj. Then the bottom part becomes y, so it's going to be 6 over h squared times sy minus yn minus 1 minus yn minus 2 sy minus y0 minus yn, and then it's going to be plus sy minus y0 and y1. So let's simplify this a little bit. So the top is 1, 2, 3, 4, 5, 6 sz, 6sz minus z1 minus zn minus 1 equals 6 over h squared, and we've got 2 sy, an sy and an sy minus 2 sy, so the sy's vanish altogether. And what happens to the y's? We've got a y0, 2 y0s and another y0, so minus 3y0. Got a y1 just occurring once, so a minus y1. Got a yn minus 1 occurring once, minus yn minus 1, and 3 yns, a minus yn and a minus 2 yn. Ooh, I messed up there. That's a minus minus. So we had plus 2 y0 minus y0, so that's a plus y0, and it's going to be a plus yn. Okay. Okay, so have I done this right? Was this really 6sz? Yeah, I guess so. So let's see. So what was the equation we had? We had that the integral, so the integral of sx, where s isn't a function that we're trying to approximate, it is our cubic spline. It is all the cubic sections all attached together. dx from t0 to tn, right? Now you've integrated from 0 to nh, which is weird because at no point did we ever assume that t0 was 0. So that's a bit strange. Making a strange assumption that t0 is 0. Don't think I need to do that. It's a typo in their work. So this was equal to trap minus h cubed over 12, and the sum from z1 to zn minus 1, so sz. Aha! And we know what sz is from what we just did. So sz is equal to 6 over h squared y0 plus yn minus y1 minus yn minus 1 plus z1 plus zn minus 1, all divided by 6 to see. So this integral here is going to become trap minus h cubed over 12, oops, So we've got 1 over h squared y0 plus yn minus y1 minus yn minus 1 plus z1 plus zn minus 1 over 6. I cancelled the 6 with that 6 there. Okay. Still not quite what they've got, but it's looking pretty close. We're getting there, I think. So equals trap. So let's take the y's out first. So h over 12, so I'm going to say minus h over 12 y0 plus yn minus y1 minus yn minus 1, and minus h cubed over 72. That's 12 times 6 is 72, so 24 times 3 is 72. There we have it. I think I might have said something stupid, that 24 times 6 was 72 earlier. Ha! It's going to be 144 here. So h cubed over 72 z1 plus zn minus 1. So is that what they've got? They have h over 12 y0 minus y1 and y minus yn minus 1 plus yn. Yeah, that's what we've got. And minus h cubed over 72 z1 plus zn minus 1. Yeah, that's cool. So in fact, we don't have to calculate the middle z's if what we're trying to do is approximate the integral this way, which is probably what you'd be using this for. I guess it's its primary use. So in which trap is a trapezoidal rule, and z1 and zn minus 1 satisfy the two simultaneous equations, which give us a z1 and zn minus 1 from before. Interpolation by spline functions is an important subject. It occurs in the storage of computer fonts, such as the one that you are now reading. Did you ever wonder how the shapes of the letters in the fonts are actually stored in a computer? One way is by storing the parameters of spline functions that fit the contours of the letters in the font. Well, that's cool. I guess it must be used in all sorts of graphics then, where I can't remember what the term is, but graphics where it doesn't matter how big you stretch the image, it's always going to have, the contours are always going to be perfect. I can't remember the name of that, but yeah, that's cool. That brings us to the end, finally, of section 1.4. Hooray! And we can finally go on to the next section. That was quite a cool section. I like that little end bit there. Maybe if I'd read that first, I wouldn't have spent so long on the previous bit, but maybe I would have. It was still pretty fun. Okay, so now on to section 1.5, two independent variables. In this section, we will see how generating functions can be helpful in problems that involve functions of two discrete variables. We will use the opportunity also to introduce binomial coefficients, since they are surely one of the most important combinatorial counting sequences. Let n and k be integers, with k between 0 and n. In how many ways can we choose a subset of k objects from the set 1 to n? Let's pretend that we don't know how this will turn out, and allow generating functions to help us find the answer. Suppose f n k is the answer to this question. So f n k equals number of ways to choose k items from n objects. Suppose f and k is the answer to the question. We imagine that the collection of all possible subsets of k of these n objects are in front of us, and we will divide them into two piles. In the first pile, we put all of those subsets that do not contain the object n. So the n objects are numbers 1, 2, 3, 4, and so on to n. So pile 1 pile 2. Pile 1 is subsets containing n, and I suppose subsets not containing n. So in the first pile we will put all of those subsets that do contain the object n, and into the second pile we will put all the subsets that do not contain n. In the first of these piles, obviously contains f, n-1, n-k subsets. So subsets containing n. So then we have n-1 of our objects that we have to pick k-1 for. So yes, it's going to be f n-1 k-1, because if we've got a subset of this set which is k elements and one of them is n, then out of first n-1 numbers here we have to have k-1 of them. So the second one is going to be f n-1 k, because as n isn't in the set, k of them have to be in the first n-1. So the first of these piles obviously contains f n-1 k-1 subsets. The second pile contains f n-1 k subsets. The two piles together originally contained all of the f n k subsets. So it must be that our unknown numbers f and k satisfy the following recurrence. F n k equals f n-1 k plus f n-1 k-1. And we have that f n0 equals 1. Presumably that's for all n. So this is essentially saying that there's only ever one way to choose n objects, no objects from a set of a set. There's only one way to pick no objects, which is the empty subset, and there's only one empty subset and only one empty set. So I'm happy with that this holds for all n. To find formulas for these numbers, we use, what else, generating functions. For each n, 0, 1, 2, and so on, define the generating function bnx equals sum k greater than or equal to 0 of fnkx. So bnx equals sum k equals 0, was it 0 to infinity? Greater than or equal to 0 of f and k x to the k. So for k greater than n, this is going to be 0. Now we multiply 1.5.1, our recurrence relation for fnk, through by x to the k and sum over k greater than or equal to 1. So what do we get if we do that? So sum k equals 1 to infinity f n k x to the k equals sum k equals 1 to infinity f n minus 1 k plus the sum from k equals 1 to infinity, and missed out an x to go there, f n minus 1 k minus 1 x to the k. So what have we got here? This first one is bnx minus the k equal to 0 term. So bnx, sorry, no, that's right, bnx minus f n0, which is going to be 1. Just write it underneath for the time being. And here we're going to have bn minus 1x, n minus 1 x minus f n minus 1 0, and this one again is going to be 1. And the last part here, as k goes from 1 to infinity, k minus 1 goes from 0 to infinity. So this is just plus b n minus 1 x. So this gives us a recurrence relation for the polynomials bn, doesn't it? So we have bn x minus 1, but we've also got a minus 1 on this side, so I'm going to cancel them out, just ignore them. So we get bnx equals bn minus 1x plus bn minus 1x, so 2. I think I've done something wrong here. I definitely have. I know what. In this one, what I didn't do was account for a factor of x. So this is going to be x times bn minus 1, I think. Because when k is 1, you've got fn minus 1, 0, x to the k rather than x to the 0. So you have a factor of x here. So we have bnx equals bn minus 1x times 1 plus x. Alright. So now multiply 1.5.1 throughout by x to the k and sum over k greater than or equal to 1, which is what I just did. The result is that bnx minus 1 equals bn minus 1x minus 1 plus x bn minus 1x for n greater than or equal to 1, with b0x equals 1. So what's b0x? b0 0x equals sum from k equals 0 to infinity of f0 k. So if k is bigger than 0, there's never any way to pick a non-zero, a non-empty subset of the empty set, and there's only one way to pick no objects of the empty set, so this is just 1. I agree with that. b0x equals 1. Therefore bnx equals 1 plus x to the n. So bnx equals 1 plus x to the n. That's fine, because every step here you're just multiplying through by 1 plus x. So b1x is 1 plus x times b0x, which is 1, so Yeah. Our unknown numbers, f and k, is revealed to be the coefficient of x to the k in the polynomial 1 plus x to the n. Yeah, that's pretty cool. I like that. To find a formula for f and k, we might, for example, use Taylor's formula, which would tell us that f and k is the kth derivative of 1 plus x to the n evaluated at x equal to 0 and divided by k factorial. The differentiation is simple to do. Indeed, the kth derivative of 1 plus x to the n is that. Let me just check that. So b, no, I'm just going to say 1 plus x to the n, which is bn, d by dx is going to be n 1 plus x to the n minus 1 equals n bn minus 1 x, which is going, so then this is going to hold for all n, so this is going to be equal to n minus 1 bn minus 2 x. No, it's not. No, it's not. Only if we continue to differentiate it. So, but the kth derivative, yeah. So dk to dx to the k, 1 plus x to the n is, yeah, so you're going to have n minus 1, and so on, n minus k plus 1 plus x to the n minus k, yeah, which is n factorial over n minus k factorial b n minus k x. Evaluating that at x equal to 0, b n minus k x is the sum of I greater than or equal to 0 f n minus k I x to the I. So when you put x in 0, you just get the constant term from this. There, f n minus, the constant term is f n minus k 0, so there's only ever one way to pick 0 objects from a set of n minus k objects, so that's 1. So evaluating this at 1, you have n factorial over n minus k factorial. Apparently we have to divide by 1 over k factorial. So n factorial over n minus k factorial, k factorial. The Taylor's formula. Why does that make sense? Why do we have to divide by k factorial? So let me think. If I had a general power series, fx equals sum from I greater than or equal to 0, I'm going to call it fi x to the ith power. And I want to find these fi's, and I don't know what they are, say. Then if I evaluate f at 0, then I'm going to get f0 as all the x's, x to the i's are 0. And the only term without an x is f0, yeah. Okay, so if I differentiate d by dx fx, It's going to be equal to I greater than or equal to 0. I fi x I minus 1. And when I is equal to 0, this term is 0, so I'm just going to go from I greater than or equal to 1, which is equal to I equals 0 to infinity, I minus I plus 1, fi plus 1, x to the I. And so if you evaluate d by dx of fx at 0, we're going to get the constant term of this, which is I, so it's going to be 1 times fi plus 1, and I is 0, so I of f1 times f1, so that's f1. Yeah, I guess this makes sense. So if you differentiate it k times, the constant coefficient is going to become the kth coefficient of your power series with k factorial before it. Yeah, because if you take the coefficient fk x to the k and you differentiate it k times, it's going to become k fk x to the k minus 1, and then k minus 1 k fk x to the k minus 2, and so on, and eventually when it becomes a constant term you end up with k factorial fk on the outside. So yeah, that makes sense. So yeah, so I agree then. So the formula is given by n to the k over n minus 1, n factorial over k factorial over n minus k all factorial. So what have they said? Indeed, the kth derivative of 1 plus x to the n is n minus 1 dot 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 n minus k plus 1 times 1 plus x to the n minus k. If we put x equal to 0 and divide by k factorial, we quickly discover that fnk is the number of k subsets of n things given by n choose k. That formula. Yeah. For integers nk with k between 0 and n. That was pretty cool. I liked that. I've never seen that proof before. And that's very easy to implement and remember if you want a proof of the binomial theorem. That's pretty cool. That pretty well takes care of the binomial coefficients n choose k when 0 is between k and n. And n and k are integers. When k is a negative integer, the binomial coefficient n choose k is 0. Sure. Although the second member of equation 1.5.3, that was the formula for n choose k written in two different ways. Firstly is n factorial over k factorial over n minus k factorial, and the second is n times n minus 1 times n minus 2 and so on to n minus k plus 1 over k factorial. So that second term is the second member, I'm guessing. The second member of equation 1.5.3 is difficult to decipher if n is not a non-negative integer. No, the second member then is the middle term, and the third member is the right term. The third member isn't a bit hard to understand, even if n is a complex number, so long as k is a non-negative integer. So that gives us an extension to the definition of binomial coefficients to arbitrary complex numbers n, namely n choose k equals n times n minus 1 times n minus 2 dot 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 n minus k plus 1 over k factorial for any integers k greater than or equal to 0. Thus, we can do things like minus 3 choose 3, which is minus 3 times minus 4 times minus 5 over 3 factorial, which is 6, which gives us minus 10, and I choose 2, which is I times I minus 1 all over 2, etc. The generating function, Bnx, remains valid for all complex numbers n. So you'd be just taking the function 1 plus x to the power of n. Why does it remain valid for all complex numbers n? Our proof that Bnx was equal to 1 plus x to the n relied on induction, essentially, on integers n starting with b0x equal to 1. So, I mean, definition makes sense, I suppose. Definition of a power series makes sense, at least. K greater than or equal to 0 and choose k x to the k. That's fine. So, I mean, yeah, that's how Bnx was defined, wasn't it? It was defined as Bnx was defined as the sum of k greater than or equal to 0, n choose k x to the k, and for any complex number n, this makes perfect sense because we can calculate all of the coefficients of that power series, but we don't know that it's equal to 1 plus x to the n, or if that makes any sense, because that relied on induction here. So they say it remains valid for all complex numbers n. The series terminates if n is a non-negative integer, and it converges for absolute value of x less than 1 in any case. Okay. Is that easy to prove? Possibly. I'm going to leave that though. What is the support of n choose k? That is, for which values of n and k is it true that n choose k is non-zero? First, k must be a non-negative integer. Yeah. If n is not a non-negative integer, then n choose k is surely non-zero by 1.5.4. Let's see. If n is not an integer, then all of the factors on the top must be non-zero, because they're all of the form n minus an integer. And if n minus an integer was 0, that would mean n was an integer. So yeah, definitely non-zero. If n is a non-negative integer, then 1.5.4 shows that n choose k is non-zero. If and only if k is between 0 and n. Yeah. Accordance with the combinatorial definition. Yeah. A very important consequence of these facts is that if n is a non-negative integer, instead of writing something like the sum from k equals 0 to n choose kx, we can equally well write the sum from k equals minus infinity to plus infinity n choose kx. Sure, because all but finitely many of the n choose k there are non-zero, because the binomial coefficients vanish on all of the seemingly extra values of k that appear in the second form of the sum. The binomial coefficients cut off the sum by themselves, so there is no need to do it again with the range of summation. Not sure what I mean by that, but I was taking k from 0 to infinity anyway. Okay, so that being the case, we introduce two conventions that we will adhere to throughout the book. Convention 1. When the range of a variable that is being summed over is not being specified, it is understood that the range of summation is from minus infinity to plus infinity. That could open a slight can of worms, because say you take two generating functions or two power series two series fx equals sum from I'm going to say from minus infinity to infinity, fi x to the I, and g x equals I from minus infinity to infinity gi x to the I. And if I was to multiply f and g together, which we may want to do at some point when playing around with our power series, you're going to get the sum from I equals minus infinity to infinity, and the sum from j equals minus infinity to infinity, fi g j minus, no sorry, it's going to be fj gi minus j x to the I outside. So coefficients of x to the I terms occur if we have a coefficient on the left hand side which is, well, if we multiply a term on one side with a term on the other side such that the sums of the powers of x equal to I, and that's everything of the form j and I minus j. So if these can be non-zero for infinitely many of these products, which will happen in this case potentially, then this might not converge and we can't multiply together, so we'd have to be careful in that case. If these were instead from 0, then this is always going to have finitely many non-zero terms, as you can take j from 0 to infinity, and once j exceeds I, then this g I minus j is always going to be 0. So it would always make sense then. So we'll have to be careful later on in the book, I suppose, in cases like that. Convention 2. When the range of a free variable in an equation is not specified, it is understood that the equation holds for all integer values of that variable. For example, we will write the sum k, n choose k, x to the k, equals 1 plus x to the n. So it's understood that k is an integer and n is an integer as well, I suppose. These conventions will save us an enormous amount of work in the sequel, mainly in that we won't have to worry about changing the limits of summation when we change the variable of summation by a constant shift. Let's look at generating functions of some other kinds. If we multiply bn to the x by y to the n and sum over n greater than or equal to 0, we find, okay, let's do this. So this is what I thought we were going to be doing in this section. So I've got two variables now, sum n greater than or equal to 0, bnx y to the n. And then they've said it's equal to sum n greater than or equal to 0 and sum k k greater than or equal to 0, n choose k, x to the k, y to the n. And what's this equal to? We can take the y to the n out. So this is sum from n equals 0 to infinity, y to the n, k equals 0 to infinity, n choose k, x to the k. Yep, and as n's an integer, we know that this is 1 plus x to the n. Sum from n equals 0 to infinity, yn, 1 plus x to the n. Okay, and they've got it, they've written it in a different form, so they've written it as, yes, so this can be thought of as geometric series with ratio y, so we can equally well write this as sum from n equals 0 to infinity, y times 1 plus x to the n, everything to the n, and so that's 1 over 1 minus y, 1 plus x. So for integer n greater than or equal to 0, n choose k is the x to the k, y to the nth coefficient of 1 over 1 minus y, 1 plus x. Yeah, that's pretty cool. Never really thought of multivariable polynomials having like an expansion, a power series expansion like this. For another exercise, let's evaluate for non-negative integer k the sum from n equals 0 to infinity, n choose ky to the n. So yes, that is different. We must have a fixed k here. So I'm going to see if I can do this easily. So n choose k, so k is fixed beforehand, fix k, y to the n. What do we know? What do we know here? Well, n choose k was the x to the k, y to the nth coefficient of this thing. N choose k. Okay, I'm just going to see what they've done. What have they done? So, note that the index n runs over all integers, but that the summand vanishes unless n is greater than or equal to k. So, the sum is clearly so they say it's a coefficient of x to the k of a let's write out this. See what we've got here. So coefficient of x to the k and greater than or equal to 0. Sum from k equals 0 to infinity, n choose k, x to the k, y to the n. So I guess I see what they're doing here. I think so. This here, this sum here, Sorry, I'm using both a lowercase and a uppercase y. Assume they're both the same. This series here is a sub-series of this series here, which is what we had earlier, and it was equal to this. It's the it's a sub-series where the x coefficients are x to the k. It's x to the k, so everything's going to have x to the k. Yeah, so when they're writing the x to the kth coefficient, that is itself going to have the variable y in it. Okay. So, and then they're using this form here. So let's see where this leads us. So equals x to the kth coefficient of 1 over 1 minus y 1 plus x. Aha. Then they've taken out a 1 over 1 minus y, and then they've divided by 1 minus y and multiplied the right hand side by 1 minus y. Okay. Why have we done that? So what do we have here? We're after the x to the kth coefficient, which itself is full of y's. We know that this thing here is equal to n greater than or equal to 0, k greater than or equal to 0. No, we know it's equal to n greater than or equal to 0, y to the n, 1 plus x to the n. So it's the x to the coefficient of x to the k of this thing. Yeah. Okay. Well, I don't understand why they're doing what they're doing, but I'm gonna try it anyway. See what happens. So they're after x to the k, coefficient of x to the k of 1 over 1 minus y, 1 plus x, and then they're multiplying, they're taking out 1 over 1 minus y, x to coefficient of x to the k, 1 over, and then I suppose you have to put 1 over 1 minus y, 1 over 1 minus y, minus 1 over 1 minus y, 1 plus x. And if we we can simplify this somehow. So they've still kept a 1 on top. So 1 minus y over 1 minus y 1 plus x. That's essentially what this is. And then dividing the top and bottom by, multiplying the top and bottom of this by 1 minus y gets us this. And they have it in form, they say that this is equal, I think this is what they're saying, that this is equal to 1 over 1 minus y over 1 minus y x. Why would that be the case? Let's multiply, is this true? Question mark. I multiply the top and bottom of this by 1 minus y. I get 1 minus y over 1 minus y minus yx, which is equal to 1 minus y over 1 minus y times got a minus 1y and a minus xy 1 plus x. So yeah, okay, this is the same. So, how do I get to it from here then? I guess if I just wrote it out as so if I just wrote that out as 1 over 1 minus y 1 plus x over 1 minus y, and try and get a 1 minus y up here, equals 1 over 1 minus, so I'll put brackets here so it's not too confusing what's going on. 1 minus y plus, sorry, minus yx over 1 minus y. Yeah, so that's equal to 1 over 1 minus yx over 1 minus y. Yeah, okay, I see it now. So we had x to the k coefficient of 1 over 1 minus y 1 plus x is equal to 1 over 1 minus y, x to the k coefficient of 1 over 1 minus y over 1 minus y x. Okay, and this is better now because we've got a single x and we can do this as a geometric series in x. So 1 minus y, I can take it from here. So I'm going to no, I can just write that straight into the form. Straight into the form. That's 1 over 1 minus y, x to the kth coefficient of sum from n equals 0 to infinity. It's geometric series with ratio y over 1 minus y, y over 1 minus y to the cat I've written from n, so to the n, x to the n. That's fine, isn't it? So the x kth coefficient is when n equals k, so we should have y to the n over 1 minus y to the n. So this is this bit here, and so we need a 1 over 1 minus y. So y to the n over 1 minus y, n plus 1, is equal to the sum of n k greater than or equal to, no, this should have been k. Oops. Sum from n greater than or equal to 0 of n choose k y to the n. That's what we started with. So yeah, we've evaluated that power series and it's equal to that. That's pretty cool. And is that what they end up with? Yeah, that's what they get. So for future reference, we will place side by side these two power series generating functions of the binomial coefficients. Sum of k, n choose kx is 1 plus x to the n. The sum of n choose k, y to the n is y to the k over 1 minus y to the k plus 1. And that concludes section 1.5. And I'm going to stop there because that's quite a long video again. And that was pretty cool. I enjoyed that section. Not too hard. Didn't take too much work. Like section 1.4 did. It took me quite a lot of work to do it in a way that I thought was thorough. So yeah, we go on to next would be section 1.6, where we look at partitions. That should be cool. I'm looking forward to that as well. So, see you next time.